Over the last few months, I've been obsessed with Pascal's triangle, but not about the properties like how it shows the expansion of polynomials. No, how you can create art out of it. The idea of Pascal's triangle is straightforward. Imagine you have an infinite row of zeros, and somewhere along this infinite row of zeros, you have a 1. Now there is one simple rule. The number between the numbers in the next row will be the sum of the two numbers above it. You can do this for however many rows you want, and these numbers have a lot of hidden secrets in them that I will not cover. The thing I'm interested in is when you color in this triangle. You can apply some simple logic to do that. We will take the mod of every single number in the triangle, and when we get a 0 from the mod, we will color it blue. And if it is not a 0, we will color it a different color, in this case green. If you don't know what a mod is, it is the remainder of doing division with a certain number. Think back to elementary school and you were just learning division, and you had to keep the remainder of the number if it couldn't go in perfectly. I will start applying this to the basic Pascal triangle with a mod 2. If you do mod 2 on 1, you get 1, because 2 goes into 1 0 times, and you get a remainder of 1. This means the color will be green. In the next row, we get more 1s, so it will again all be green. In the third row, we have a 2, which with mod 2 gives us 0, because there is no remainder. This means it is blue. We continue doing this until you reach the end of the triangle. Doing this by hand is obviously very inefficient, so I made a program to do it for me. We can do any mods we want, and by doing that we can see a few patterns. The first pattern is with the primes. Mathematicians love the primes, and they have some interesting things which you can see with mods 5, 7, and 11. I'll also show you powers of 2 as well, because programming is all about those powers of 2. You can also always guarantee that a triangle will end in an all-green row. With even numbers, just have the number of rows be a power of 2. With an odd number 1, it depends. A rule of thumb is that if you take the mod number to a power of itself, it will end in a full row, though this sometimes can make really big triangles. So you can find out the length of the first full pattern and then multiply it by an integer to always end in a green row. Those are all cool and all, but after a while they get quite boring to look at, don't you think? Well, what if instead of just one number being in the starting row, we have 2 spread out in the beginning with zeros in between them? The same rules still apply, but now at some point the 2 triangles will intersect. This can be found by the number of zeros between the 2 starting numbers. For example, 4 zeros in between the numbers will mean they will intersect 5 rows from now. 5 zeros means 6 rows from now. The intersection point is always n plus 1 rows from the beginning, and in row n plus 2. This makes sense if you think about it. Each row is 1 bigger than the row above it. If you play around with this though, you will find that sometimes the design is the same, even though you're using different numbers. This is because of the mod. When you apply a mod to a large set of numbers like this, all of a sudden you are not doing normal addition. You are doing mod addition. When applying a mod to a number, the mod will spit out a number from 0 up to the mod number minus 1. This is because if the mod reaches the mod number, then it resets to 0. Let's try out mod addition on a normal Pascal's triangle with mod 2. We can apply the mod to the first number and we get a 1 back. 0 plus 1 equals 1, so we get 1s in the next row too. The row after that we get a 2, which becomes a 0. In mod 2, 1 plus 1 equals 0, and 0 plus 0 equals 0 as well. In the next row we get all 1s, and you can keep doing this as far as you want. Hopefully now you can see why some of the numbers give the same design even though they are different. Using the example from before, in mod 5 addition, the 7 immediately becomes a 2, thus making the addition the same as a 2, 0, 0, 0, 0, 3 intersecting Pascal triangle. This means that in order to efficiently create new designs, you should pick numbers under the mod number, as a number above the mod number will just give you a number below it with mod addition. Another thing you might notice playing around with this is that if you put a mod number as one of the starting numbers and 1 as the other number, then you will just get a normal Pascal triangle with that mod with a giant blue stripe on the side. This also has to do with mod addition, because you are pretty much inserting a 0 as one of your starting numbers by putting in the mod number, thus simplifying the triangle down to a normal Pascal triangle. The final triangle I did was a triangle being intersected by an upside down triangle. Now that sentence probably made no sense, so let me do this with a short example. We are going to have 2 Pascal triangles, one acting normal and one going upside down. We're going to have them intersect at row 3, so we get this batch of numbers. Now the top triangle absorbs the bottom triangle by following the normal addition rule, but adding the number in this space if there already is one. So the next row, instead of being 1, 3, 3, 1, will be 1, 4, 4, 1, because the 2 3's absorb the 1s there. In the next row, we will get 1, 5, 9 because the two 4's added together absorb the 1, 5, 1. A conjecture I am going to make with this strategy is that every triangle is unique because the row where they intersect will always be different, and the numbers being absorbed will always affect different numbers. You know the drill by now. Take a mod and apply it to all of the numbers. With this, you get a normal Pascal triangle design up to the point of intersection. Then the numbers start to change. This is more pronounced on larger triangles. As stated before, every triangle is unique, making every design different. Adding just one more row could change the design of the entire triangle. My personal favorite are the triangles that have a centerpiece in them. I can't really find any patterns in these designs, but they are cool nonetheless. I hope you enjoyed looking at all of that art. If you want to see more, I posted some of my personal favorite designs on my Instagram, link in the description. See you in the next video.